everybody. Today we're going to work on one example only of a rational function, but we will find everything that your teacher might ask you about this one rational function. So just a little bit of background on the rational function is the parent function is just 1 over x. So if you were to graph, it looks like that, okay? And the vertical asymptote is the vertical line right there that your graph approaches, but will never touch that line. It's going to be an x equals line, vertical asymptote. The horizontal asymptote is the horizontal line or the y equals line that goes from side to side that your graph will approach but will never touch that line. The asymptote is just an invisible line that your graph is approaching. Okay, just a little bit of background. So let's get started. If I need to find the domain, and that's one thing that we're going to start out with. Let's find the domain for this function. Remember, when we think about domain is all the x values that this function will provide to you. When I look at the numerator, I immediately think I need to factor it. So over here off to the side, I'll go ahead and factor. So I'm going to think of two numbers that I multiply and give me 10, same two numbers that multiply that I add, and then I get 7. So 2 and 5. 2 times 5 is 10. 2 plus 5 is 7. So x plus 2, x plus 5, and here just x plus 3 in the denominator. Okay, so going back to domain is all real numbers that my function will give me about the x values. So when you think of domain is x. And it's like, okay, so if I am to put this in the graph, and I can see that the graph goes on forever over to the negative infinity side, go over all the way forever on the positive infinity side. But then I know there's something right there in the middle that I don't know what it is. And that's what we need to find out first. So before we find the domain, I will find the vertical asymptote first. And then we're going to find how they relate. And next, we're going to find the hole in the graph. Okay, so just because I will go ahead and plug in that function in. And it doesn't matter if you want to put this one in or that one, it's the same thing. So by eyeballing the graph, I know there's definitely a vertical asymptote right there somewhere. See that my graph is approaching that one vertical line. By eyeballing it, it seems to be right there at -3, but I don't know. We're going to find out. And I do not have a horizontal asymptote, but I do have an oblique asymptote. It's a line right there. I didn't mean to write on my calculator. It's right there. We will calculate that too. So at least right now, my eyeball tells me that it should be right there somewhere for the vertical asymptote. Okay, how do we find the vertical asymptote? So the vertical asymptote is the easiest one for you to find. You're going to get the denominator right there and set it equal to 0 and then solve. So the vertical asymptote, I have x plus 3, set it equal to 0, and you solve. So when you solve, you just minus 3 from both sides, and you have that the vertical asymptote will be x equals -3. So, sometimes eyeballs are good. And it turned out that it was really easy to find just by eyeballing. But next time, if you don't know, just go ahead and get the denominator, set it equal to 0, and that's going to be your vertical asymptote. It has to be x equals because the asymptote is a line. Okay, it's a line, not a point. It's a line, so it's x equals. All right. Now a hole, it's a hole in the graph to where your denominator makes it equal 0 or makes it undefined. So a hole is a point on the graph where the value of the function is undefined. So undefined is when you divide that by 0. So when I was looking for the vertical asymptote and I set it up to equal to 0, that will immediately give me the hole in the graph. So the hole in the graph will be right where x equals -3. Okay? All right, how does all this relate to domain? Domain is going to be everything. So look at your graph again. Notice that your graph goes all the way over to -infinity, all the way over to +infinity, except for that one line right there. Okay, so you have two ways to write it out. So the domain is all real numbers except x equals -3. You can also write it out as x does not equal -3, or in interval notation will be from -infinity, does not include -infinity, all the way up to -3, does not include -3, and then in conjunction with -3, all the way over to +infinity. I made a boo-boo here. It has to be non-inclusive over here, so it's not brackets, it's just simple parentheses, okay? I couldn't find my whiteout. Okay, so now that's way better. So it approaches -3, but does not include -3, just because we said that right there. Okay, now that we're talking about domain, we will find x-intercept. So the x-intercept you can find from the graph, so it should be right there at -2-ish, and that one right there at -5. Oh, that -5 landed right there. But let's say that you don't have the graph, but you can solve it by hand. So x-intercept, you're going to have a number for x, y is 0. Okay, so y is 0. I'm going to do it by hand just because that's what we do. So if y is 0, I'll make that equal to 0. And I will use the factored way just because it's halfway done for me. So for me to find the x-intercept, y is 0. So I have x plus 2, x plus 5, everything over x plus 3. So at this point, I multiply both sides by x plus 3. It's already there. So now you already know that everything multiplied by 0 is 0. And this, I can simplify numerator and denominator. I can mark that out or simplify down to 1. And this is 0. Okay, 0 equals x plus 2, x plus 5. Now I will set each factor equal to 0 and solve. So this is a factor, this is a factor. So I have x plus 2 equals 0. You minus 2 on both sides. You have one x-intercept is -2. The other one is x plus 5 equals 0, minus 5 from both sides. You have x equals -5. So the other x-intercept, I have that right there, -5. Okay? Since we're talking about intercepts, let's find the y-intercept. If I know the x-intercept, the y is 0. For me to find the y-intercept, the x is 0. Okay? You have, if you go to the table, It's just easy because it's right there. Okay, x is 0, y is 10 over 3. But let's say that you don't have a calculator or you just flat out didn't think about that. We can just substitute x into the function. I have y equals x squared. No, I'm going to use the factored way. X plus 2, x plus 5 over x plus 3. Okay, so here we go. I will plug in 0 for x. 0 plus 2, 0 plus 5 over 0 plus 3. 0 plus 2 is 2, 0 plus 5 is 5, 0 plus 3 is 3. Here I have 2 times 5 is 10 over 3. Voila, exactly what I was expecting to find. And that's what I have in my handy dandy graphing calculator right there. So 10 over 3. Now, the last thing we need to do is to find the horizontal asymptote. Horizontal asymptote. And I think it's going to take another 10 minutes. And I'm sorry, okay? I am very sorry. Now, I have a little cheat sheet over here that I've used for years. If you had me for Algebra 1, you probably remember. So the trick here, you will compare the degree of the numerator and the denominator, okay? So you're going to find out the degree of the numerator. So if the degree of the numerator is greater, then you have no horizontal asymptote. Now, if the degrees of the numerator and the denominator are the same, then you're going to get the leading coefficient of the numerator and divide by the leading coefficient of the denominator. But then if the degree of the denominator is greater, then your horizontal asymptote will be right there, the x-axis. So let's see which one of these can I use for our example that we have. So the degree of the numerator is 2. The degree of the denominator is 1. How do I know that? Well, you have to look at the exponent right there. So the highest exponent, that's what determines the degree of that one expression. So the degree of this one is 2. The degree of this one, when you don't have anything, it means it's 1. So 2 is definitely greater than 1. So 2 is greater than 1. That means the degree of the numerator is greater. When the degree of the numerator is greater, then I'll look it over here. The degree of the numerator is greater. So that means I don't have a horizontal asymptote. And you're like, hey, I did all this work for nothing. So the horizontal asymptote is none because the degree of the numerator is greater. That leaves me with the slant or oblique asymptote. And that's what we're going to calculate. Slant or oblique asymptote. How we're going to do that? For us to be able to find that, you're going to have to divide. I'll write it out for you. So you have to divide the numerator by the denominator. You're like, how am I going to do that? Well, long division. Yes, you've been so used to using synthetic division, but long division, it's not bad. It's actually very doable. So here, the denominator is x plus 3, goes over on that side, and then you divide by x squared plus 7x plus 10. And we're only using the quotient to write out the equation of the slant asymptote. So we're going to do x squared divided by x. You get x. X times x is x squared. then I have x times 3 is 3x. You put that in parentheses, and then you're going to subtract. So x squared minus x squared, 0. That's good. 7x minus 3x, 4x. Bring the last one down. And then we do it again. 4x divided by x is 4. Now you multiply. 4 times x, 4x, plus 4 times 3 is 12. Put that in parentheses and find the difference. 4x minus 4x is 0. 10 minus 12 is negative 2. Negative 2 is your remainder. And I said your equation is just the quotient. So the equation of the asymptote is the quotient of when you divide the numerator by the denominator. Voila. So your slant asymptote is y equals x plus 4. You don't believe me? That's good because you shouldn't. Check this out. So hand it in the calculator. I'm going to go in y2 and I will plug in this slant asymptote I just found. Look how beautiful that is. Okay, so that slant asymptote or oblique asymptote is the line that your graph is approaching, but is not touching it. Okay, I know it's a long video, but let me know how you went. I hope you get 100 on that assignment, and then I'll talk to you later.